structure like that. Because then again, it is something that you need to explore. You know, if you have being that sort of just sticks out of wall, stresses at the base of it will be much higher.
Yeah.
So if you sort of stick it out of the wall, then you provide like a support like this. Like that. You could go a little bit smaller in size. So we don't know until we try. But obviously you don't want it to be collapsed. Yeah?
So as long as the stress can pass.
Not all displacement should be minimal. Okay? So it is good, you can allow a little bit, not too much. But it's a crane, more or less. Yeah? So it's a pulley, you use this to lift things up. So if your crane does that, it's not a good job. This is just like a design here. In the abacus you can't do that.
We don't need to find like a critical bucket.
So a good question here. This is straight out of design textbook. So it's more geared towards design, but you know, you don't need to worry about buckling and finding critical buckling and all this stuff. But what we can do here, just like remodel this, do the sizing, making sure that tip doesn't move, and then figure out, because the whole idea of this exercise is also give you opportunity to play around with different sizes. So not all of them need to be of the same size. Yeah. So for example, this one here needs to be a little bit stronger or thicker than that one there, for example, or other way around. Yeah. So what you will do, you assign same for all of them. You run it and see what's happening there. You'll see some are red, some are blue. Those that are blue, they're probably too big, so you make them a little bit smaller. Those that are red, make them a little bit bigger, and so on, and you find optimal size. That's basically what they ask you to do. Cheapest and the lightest design. Yeah?
So what was your truss size? The truss size. The truss size.
You have to determine. That's the whole point. Yeah. You start off with the value, and then we try to find what is the lightest option. Yeah. That's right, just run it off. I fix everything initial, then I make them what they're supposed to be in the actual step. So, for example, with the timber, so if you load it along the grains, if you load it across the grains, it will be different. So the composites as well, in the composite materials, when you've got a fibers here, you've got a different behavior. So you can do that. For us, it's homogeneous, it's like steel, it's the same in any direction, so you don't need to do it. Yeah, for us, for wood, for composite carbon fiber, things like that, it makes sense. Okay, so here's the thing. So I just put some random values in. Yeah, small profiles, all the same, and to see what's happening there. And we got stresses that are ridiculous. They are in 60 gigapascals. So obviously it's too thin, but that's good for now. The other thing that we can check is deflection, and deflection is huge as well. But let us go now back to stresses, yeah? And see what's happening there. Now, if we, in this case, we had all same cross-sectional area. So trusses are all of the same size. And obviously, based on their position, stresses in them will be different. Yeah? So what we can see from here is that this one here and that one there, they are stretching a lot. So stresses in them are really high. It's compressive stress. See, minus is compressive, plus is in tension. This one here is also very high. It's red, so red and blue are problem, yeah? Everything else, is okay. So we know that this one and that one and that one need to be really thick, or thicker than any other. So they are most important parts or trusses in this structure. So in the second iteration, we'll go that. We'll say, let us give a special size to those 3 ones and see what happens there. Yeah? What are we going to say? We give it like, I don't know, let's say 300. Okay, so it was partially successful, yeah? So those 3 are no longer red and blue, but the other ones are a little bit bigger. So it means like the overall thing needs to increase a little bit. And that's basically what we're trying to do. That's what the point of this activity is, yeah? Again, this question is not going to be on the exam. This type of question where you need to do too many iterations. This is just practice for you to play around with, yeah? But what we can get from this, it says recommend common structural shape and size. So what we did before was sizing exercise in order to produce cheapest and lightest structure. So, you can go with the big numbers, but that will be expensive. So you have to go reduce or start with small and start adding where you need. It doesn't really matter which way you go. Constraints are that minimum is sort of your below yield stress by factor of 3, and which means like 1/3 of your yield, and there should be no displacement. Yeah. So it's basically trial and error, trial and error. Yeah. is 300, and your limit on stress would be 1. Yeah, but you don't put in yield this. You have to, let's say if you use particular alloy, particular steel, how does you work on yield strength? 300, 250.
Minus 500 plus, right? So that's what third of that, right?
Third of your yield.
So if you're assuming that we're looking at 800, so I still need to remodel it like below 100. Right?
And on the deflection. So your first challenge is to sort out the stress.
That's right.
Okay, so I'm after winning combination. So hopefully someone will be able to read out what are the sizes of each of those trusses that meet requirements. It's a bit of a challenge, I guess, or competition.
其他的你就在窗帘做到3点So you need to take your use reference from the material which is example so you do short so then your material strength your landing strength cannot that further
I just changed my boundary
Millimeter. 35 off. That would be 1/3 of your yield. So if your yield was 300, then it's okay. Pardon? It's a different problem, isn't it? But I mean, it's just as a part of exercise, it's okay.
No, if it comes in the example, I draw like this.
Yes, yeah. Okay, let's go, let's finish this. Sooner we finish, sooner we go home. Has anyone managed to solve it yet? Do we have size for 1, 2, 3? All of them? Not yet.
your previous section, is everything on the class?
I need to go back here.
Sorry, should have opened you. Now, I guess you can finish that off at home and at some other time. But let's move on to this sort of sub question. You see that problem, same problem that we got here, and designers decided to use trusses to build it. And the assumption is it's going to be cheaper, easier to assemble, and so on. Yeah? Now, if we are to do the same job, but using beams, how would that look like? So essentially, what do we have? We have this pulley that is there, and around which we got a cable that runs, connects to this crate or whatever that is box. Same thing here. And over here, we got a wall against which the structure is landing. If we have the same setup, but we are used to use beams, how would that design look like? Yeah? So this is very similar to your project. What are you doing there with the conroy? Said, okay, now we've got the same situation. How are we going to solve it using trusses? And how are we going to solve it using beams? Here, we got this lift, and that's what's shown there is using trusses. Here, how are we going to solve it using beams? What would be most obvious solution? Here. The easiest one would be to run a beam that goes like that. Yeah? And we put, I don't know, let's say profile like that. Yeah? And we have to just size it right. It will do exactly the same job as what this structure does. What you may find out if you model that the size of this needs to be really big and it's heavy. So what would be the other thing that you could do to sort of simplify it a little bit or reduce the size of it? You may add, for example, another component like that. So just imagine what we had is this. Like that, and you've got a load attached to it. Yeah? So most of the stresses will be happening at the base. But if you add something like that, so this will help a little bit with that beam over here so that it does not need to be as thick. So you can see how that design exploration increases. We are adding components, and you may do something else. You may even have another bit that goes like that. I don't know. So the idea is to reduce the weight of it and therefore cost. But then you may argue, look, more components that are added, I have to weld here, I have to weld there, I have to do those things. Well, that's something we can balance out the costs of manufacturing. And that's basically what FEA engineers do. So here's the problem. Let me come up with a design. Let me size it appropriately, and along the way to make sure that it's not too expensive. Yeah? So maybe we can, because we don't have answers for that yet. So maybe for at home, before tomorrow, so the first thing tomorrow, we can go through this again. So we figure out how much this costs in terms of what is the volume, what is the mass of the material that we need to buy, and then find a solution that does this in beam and see whether we can make it cheaper than what is here. Yeah? Are we clear on this? Do we sort of understand the idea? Yeah? So your exam is going to be, as I said, similar to this. I'm not going to ask you to do so many iterations. As I said, this is just practice. But you will be asked to say, okay, given this scenario, given this description of the problem, what is the boundary condition, what is the load, what is the appropriate element, what is the appropriate element size, and so on. What commonly could happen, and happens all the time, is when it comes to structures like this, we've got people, students, putting nodes there and there. And their structure all of a sudden looks that, you know, becomes wiggly, you know, like that. And they said a structure failed. Structure did not fail, it was you who failed, who didn't model that right, yeah? So be mindful of those things. So that is the decision that you have to make. You know, what is the appropriate element size, yeah? Same goes with the beams, that story. Remember that story of, you know, having beam or having coin. That will be also something on a test. If you make beam elements too short compared to cross section, again, it's your failure as FEA engineer, not modeling that right. So small things like that. That's what we're going to look in your submissions. Yeah. Okay. Now, before we wrap up, questions on your project, because yesterday we stayed a little bit too late explaining bits and pieces. So, are there any other questions about that? Extension will be given till 1st of April. That was what we agreed on last night. So I have not updated Canvas yet, but we'll do that. Yeah? So remember what you need to do, yeah? Yeah, so reason why you're given extension is because of potential misunderstanding that was here. So you'll have conrod design, and you have to do design using trusses, beams, 2D solid, 3D solid. Same story. You do sizing, one iteration, then you come back and improve it, second iteration, and so on, till you find solution that complies with the design requirements. Yeah? So overall, you will have at least 1, 2, 3, 4, at least 8 designs, but probably more. You know, because assumption is that if you get it right after second iteration, you're finished it. But you probably have to do more than one. Similar to this problem. Very similar to that problem, yeah? We didn't get it right after first attempt, so we tried several times, yeah? So, by doing that, you'll have more experience using Abacus, and that's basically how you learn. You know, if you build 200 models, you'll be more experienced than if you build only 3. And that's basically where we're going with this. Yeah? Yes?
So for the 2D solid elements, it was mentioned the plane strain and plane stress. So we only need to do 1 each.
One which is relevant. Yeah?
One of each that is relevant.
So I mean, like we do 1 plane stress and 1 plane strain should be the minimum requirements, right?
Yeah. It's a good question. So, when it comes to 2D solid, look, I can't yell anymore. When it comes to 2D solid, you've got 2 options: plane stress or plane strain. You have to choose appropriate to your problem. Not everything can be plane stress, not everything can be plane strain. Yeah? And you have to differentiate between the two. So that's why I didn't say here, use plane stress or use plane strain. It's like, use 2D solid and listed there options. So you have to choose what is the correct, appropriate modeling type. If you want, you can choose the other one and see what the difference is. Yeah?
But is it okay if we don't use both of them, we just use 2D shell?
There's no 2D shell. So that's another thing. So shell, although it is represented in 2 dimensions, is 3-dimensional object. Yeah? So if you got so when we talk about when we talk about 2D solid, like when you got a structure, like this, so 3D box. What are we doing as a 2D solid? We are taking front of it, and then we are saying we are ignoring this bit, third direction. And we are saying we can ignore that because all the action that happened in this plane, and everything else continues is the same through that thickness, through that direction. Yeah? So when we say plane stress, it means all the stresses are here in a single plane, and here is a zero stress. Sorry, zero stress. So there's nothing happening in that third direction. That's what the plane stress is. Plane strain is the same story. Strain happens in a plane, and there's no change of thickness through that. So that's the difference between them. Now, when we're dealing with the 3D shell, if you have a solid that is thin, that's got one dimension much smaller than the other two, like this. Like this is perfect example. That's shell. Yeah? 2 dimensions much bigger than thickness. What do? Commonly, we model middle surface. Now, surface as object itself is 2-dimensional, but lives in 3-dimensional space. 2D solid lives in 2D space. Shell lives in 3D space. So imagine this that's got a 0 thickness, but it lives in space. Yeah? 2D solid doesn't live in 3-dimensional space, lives on a screen only. Yeah? That's a major difference. What shells do, they're really good at taking loads that are perpendicular to them, like this. Shells, they don't like to be loaded like that, like this. Yeah? If you got something that is like this and you load it, shells love it. Yeah? They can deal with the structures like this, but they are not designed for it. Yeah? And we can do that. I mean, we can explore that and see what will happen if we model this as a shell. But you will see that it needs to be loaded like this. It's not going to be like that. Yeah? So that's the difference. So shell is 3D object, lives in 3D space. 2D solid lives in 2-dimensional space. Yeah? Does that make sense? So there's no 2D shell. That doesn't exist. Okay. Now, any other questions about your project? No? Or you want to go home, you're sick and tired of me walking in yeah. So let's do that. Let's go home then. So tomorrow, 2 o'clock, yeah? We'll have probably 2 more tasks, design activities, and that's it. You'll be ready for your exam.